Okay, in this lecture, we're going to talk about serial dilutions. So before we start, let's talk about some key terms. First term I want to talk about is solute. And solute is a substance that is dissolved in a solvent. For example, when you dissolve salt in water, salt would be the solute. Water would be known as the solvent. And a solvent is a substance that dissolves the solute. And as a result, we would get a solution that you see on the right. Again, water would be an example of the solvent. A solution is also known as a special type of homogeneous mixture composed of two or more substances, such as salt and water in this example. And homogeneous simply refers to a substance that is consistent or uniform throughout its volume. So that's really important to understand. When we are making solutions, we are assuming a uniform mixture, and we do everything we can in experiments to make sure that we have a uniform distribution. Because if we don't have a uniform distribution, it can throw our experiments off and they will not be as consistent. So we always want to make sure we mix our solutions and they're homogeneous. Concentration refers to the amount of a given substance contained within a solution or in a particular volume of space. It says it's the amount of solute per unit volume of solution. So if you look at the figure to the right, notice the concentrated solution, you see more particles in that small volume of water. Whereas if we have a dilution, we will decrease the concentration of the solute. So if you look at the beaker on the far right, notice it says it's a dilute solution. In other words, you have less particles in that water, so you have less particles per volume. Dilution can be accomplished by mixing with more solvent, so you can add more water to the solution, just like you see in the figure here to the right. Before, you had a higher concentration, your solution is darker in color, but if you add water, it's going to get lighter in color because you're increasing volume. You're keeping your solute concentration the same, so as a result, the color thickens out or thins out because you have fewer solute molecules per unit volume. In other words, you have a lower concentration after you add more solvent. It's no different than if you have Kool-Aid and you add a lot of water to it, it gets lighter. So it says to dilute a solution means to add more solvent, without the addition of adding more solute, of course. And it says the resulting solution is thoroughly mixed, again, because we want equal distribution, like I mentioned earlier. So let's suppose we have container 1, and container 1 is our concentrate. In other words, it's like our serum, or it's a concentrated substance. And let's say it has a 10 milliliter total volume. And notice I have 10 particles in there. Now, ideally, you would have a dark liquid. And I'm representing that dark liquid as 10 particles. So I'm using the particles as more of an illustration to give you an idea of how dilutions happen. But don't think of it as actual individual particles. Think of it more as a dark liquid. So let's say the total volume of our concentrate in container 1, we would call our concentrate. We call it our concentrate, or we could call it our starting serum, whatever. Or we could call it our solute. Regardless, let's say the total volume in container 1 is 10 milliliters. It says also we have 1 particle per milliliter. Okay, so if we were to look at container 1, and we were to take out a small milliliter here, then if we took 1 milliliter of fluid out of container 1, we would expect to have 1 particle in 1 milliliter, and that's assuming that it's equally distributed. Okay, if we have 1 particle per milliliter, then in 10 milliliters total, we would have 10 particles. Also, we would call that a 1-to-1 ratio, because if we have 10 particles in 10 milliliters, that's 1-to-1. If you divide 10 by 10, you get 1. So we will refer to that as a 1-to-1 ratio. Now, let's say we add the 1 milliliter in this small tube at the second arrow. Let's say we add that to container 2. And let's say container 2 was at 9 milliliters, but we add a milliliter with that one particle, and we add it to container 2. Now we have one particle by itself in container 2 with all the water. So we just diluted that. We just made it our first dilution by taking out 1 milliliter in container 1 with that one particle and adding it to container 2. And notice it says at the bottom, it says, and of course the arrow's pointing to container 2, but if you look under container 2, we have 1 milliliter, which contains one particle, divided by 1 milliliter, which contains the one particle, plus the 9 milliliters of our diluent, or our water. So we just made a dilution, and if you look at that, you notice we have 1 milliliter. It says 1 milliliter containing one particle divided by 1 milliliter containing one particle plus 9 milliliters of diluent. So that would be 1 out of 10. And we call that a 1 out of 10 dilution. But let's keep going. So looking at container 2, again we have, like I said, we have that one particle. But that one particle that we see can also be represented or broken up into smaller particles that are, instead of them being one particle, they're broken up into 10 0.1 size particles. And that would make our new concentration at 0.1 particles per milliliter. So in other words, if we were to take out 1 milliliter of this new dilution, if we took out 1 milliliter, instead of having 1 particle per milliliter like we did in container 1, we would now have 0.1 particles per milliliter. So we just made our dilution. We went from 1 particle per milliliter to 0.1 particles per milliliter. So we just made a 1 to 10 dilution, because in order to get back to 1 particle, we would have to take all 10 milliliters of this out of this new dilution. We would have to take the full 10 milliliters out just to get back to 1 particle that we had. Now, hopefully that makes a little sense. I do have some problems I'll work also to try to help drive this home. But again, if you look at container 2, it's also meaning that that one particle that we took out is mixed. It's dispersed amongst 10 milliliters. So it would look more like the image to the right with the smaller particles. But again, we're using particles just to drive an analogy. So in summary, we would have container 1, which has 1 particle per milliliter. We would take 1 milliliter out of container 1, and we would add it to 9 milliliters of diluent in container 2. And the 9 milliliters would add to the 1 milliliter to form a total of 10 milliliters. But the particle that we had in the 1 milliliter that we added to container 2 would break up or get dispersed into particles of a size of 0.1 milliliters. Or I just say 0.1. And the fact that they're broken up to that fraction would make that known as our multiplier. We could call that our multiplier, which is where we will mention multipliers when we do our serial dilutions shortly. Also, notice that when we took the 1 milliliter out of our container 1 and poured it into container 2, we call that an aliquot. So in summary, it says we started with a concentration of 1 particle per milliliter in container 1, and we diluted it to 1 whole particle per 10 milliliters. So we took that 1 particle, added it to container 2, and we diluted it to 1 whole particle per 10 milliliters, which means we made a 1 to 10 dilution. It says thus we carried out a 1 to 10 dilution. or we dilute it by a fraction of 0.1, which means in order to recover one whole particle from container 2, we would have to take out 10 milliliters, because we have 0.1 particles per milliliter in container 2. So we would have to take 10 of those out in order to get that one whole particle. It also says, notice that 1 milliliter per 10 milliliters equals 0.1, which is known as our multiplier. And also, in order to drive home the point one last time, again, notice we have container 2, which was diluted to a new volume of 10 milliliters of one particle. Again, we represented it. It's better represented as 0.1 particles per milliliter. So notice when you look to the right, you have container 2, where that one particle is broken up into 10 smaller particles, and instead of it being those smaller particles would be 0.1 milliliters instead of and I don't want to say 0.1 milliliters. It's better to just say 0.1 in size versus the one whole particle that you had. So think about that one whole particle in 10 milliliters as being 10 small particles, which are a size of 0.1. Okay, which is why I have the particle on the left bigger, and then the particles on the right in the other container, which is still container 2. I just represented it as, I represented that one big particle as 10 smaller particles, and each size of those smaller particles is 0.1, whereas the size of that one particle will represent 1. And what we did here at the bottom is, if you look at the 10 parts, what I'm basically saying is, if you take those, if you take container 2 and break it up into 10 1 milliliter parts, each part would have one particle in it. And of course, those one particles would measure 0.1 in size. But if you add all 10 of those particles up, you would get one whole particle in 10 milliliters, just like you have in the image to the left. So at the bottom it says the 10 parts above can be summed or multiplied to give one whole particle. Okay, or we have 0.1 particles times 10 parts, which will give us one whole particle. And it says, so we have one whole particle to a 10 dilution, or one whole particle to a small 0.1 particle dilution. So we will call that a 1 to 10 dilution. So the next question says, if we have 2 ounces of concentrate, how could we go about creating a 1 to 15 dilution? In other words, how much diluent must we add to 2 ounces in order to get a 1 to 15 dilution? There's a few ways to solve this. One common way is to set up an equation. So you could say 2 over x. I can draw that a little better. So we have 2 ounces over x. X is our unknown, ounces, is equivalent to the ratio of 1 to 15. And if we cross multiply, we would get 15 times 2. So you would just cross multiply 15 times 2 ounces is equal to, cross multiply x with 1 is equal to x ounces. And you can solve. 15 times 2 is 30 ounces, which is equal to x ounce. So the answer is, so x would be equal to 30 ounces. So in other words, we would have to take, in order to get a 1 to 15 dilution, we'd have to take 2 ounces to 30 minus 2 ounces, because you have to subtract your ounces here. So 30 minus 2 would be 28 ounces. So in summary, you add 2 ounces to 28 ounces in order to get 30 ounces of a 1:15 dilution. 1:15 dilution. And you can also think about it like this. You can say if we have 1:15, this is a way of checking your work. And one part is, you can think of 2 ounces as being one part, and you have 15 other parts. And what you can do to figure that out is you can multiply 15 times your 2 ounces, and that will also give you 30. So that's a 1:15 ratio. Also 2:30 is also a 1:15 ratio. Just an additional way to think about it. Common mistake is that a lot of people will add 2 to 30 and they would get 32. But remember, our final concentration, our final volume is 30 ounces. That's our 30 ounces. So that's the final volume in order to get the 1:15 dilution. So according to this problem, it says let's make a serial dilution across 6 containers. Container 1 contains 10 milliliter of concentrate or solute, and it says containers 2 through 6 contains 5 milliliters of diluent each. What is the final dilution in container 6? So we're starting with 10 milliliters of concentrate, and we have 5 milliliters of diluent in each container. Note the color difference. And looking at this by default, you could see that we essentially are halving our concentration each time. So what we're going to do is we're going to make a serial dilution, and we will take out 5 milliliters each dilution. So let's take 5 milliliters out. And this is called a double fold because we're essentially halving each concentration. So if we take 5 milliliters out, what we will have here is 5 milliliters of our solute into a total volume of 5 milliliters that we take out of here, plus 5 milliliters that was already in this container. That would be a total of 10 milliliters. So that gives us, if we reduce the fractions, 1/2, which is a fraction of 0.5, which we can then call our multiplier. So right now we have our first dilution, and again this is known as our multiplier. So we can multiply this 0.5 by 5 to get our next dilution. So let's say once we add 5 milliliters in container 2, this is container 2, if we mix that and then take another 5 milliliters out and add to container 3, we would then have this multiplier, which is 5 times 0.05, and that would give us 2.5 because we're basically halving our concentration of solute. So now we have 2.5 milliliters over a total of 10 milliliters. Now, again, we're adding 5 milliliters, so we still have a total of 10 milliliters, but because we solve for our multiplier, that has given us, this multiplier gives us the concentration or the amount of solute that's in our, that is going to be in tube 3. So that's the total amount of solute there. And we can reduce that, and we can have, let's just reduce the fraction. This would give us 2.5 divided by 10 would give us 1 to 4. So we could call that a 1 to 4 dilution. 1 to 4 dilution. This would be a 1 to 2 dilution. And we can keep this up. And this 1 to 2 dilution makes sense because you basically halved your first. So this would be, say, a 1 to 1 if we were to think about it that way, because it's 1 to 1. It's a whole concentrate, whereas this has been halved. So we have 2 parts, but we only have 1 part that is our solute. So 1 part solute to 2 parts total. It's a way to think about it, whereas here we have 1 part solute to 1 part total solute. And here we have 1 part solute, which is the 5 milliliters, to 2 parts, which includes the solute and the diluent here. So it would be 1 to 2. You can think about it here, 1 to 4, we would have 1 part, which is our 2.5, and the other 3 parts would be our diluent, which would complete the 1 to 4. So just to give you an idea, up here, let's say for container 3, for 2.5, you can imagine we have, let's imagine we have 1, 2, 3, 4. Let's imagine this container is broken up into 4 parts. So there's 4 slices here. Well, 1 slice would make up our 2.5 milliliters worth of actual solute, S-O-L-U-T-E, that came out of here. And the other 3 2.5s would be our diluent, which is just water. But we have a total of 1, 2, 3, 4 parts. So this is 4 parts total. 4 parts. It's 4 parts total. But 1 part out of the 4 total parts represents our dilution. Okay. So that's a way to think about it also. So let's also use our multiplier of 0.5 that we got in the first step. And again, we added 5 milliliters from tube 2 to tube 3. So we're going to take 5 milliliters, we're going to mix this, and then we're going to take 5 milliliters out of tube 3 and add to tube 4. And by using our multiplier, we could say 2.5 times 0.5 is 1.5 out of 10. And if we reduce that, we would get 1.5 out of 10. Actually, this is 1.25. Sorry, it's 1.25. So we get 1.25 out of 10. And when you get a weird number like this, you can also flip it. This can also, just to make the whole, in order to make the ratio make more sense, you can also flip the term and that will give you 8 over 1, which is equal to, this is equal to a 1 to 8 dilution. So that's 1 to 8 dilution there. Let's see. Let's again repeat the process. We mix and we take 5 milliliters out. We use our multiplier again, times, this is times 0.5. So 1.25 times 0.5 is 0.625. And we divide that by 10, and we can also flip this. 10 divided by 0.625, which gives us 16 over 1, which is, running out of space, which is a 1 to 16 dilution. We could take it one more step. Take 5 milliliters out. Use our multiplier. Don't have much room here. Times 0.5 is our multiplier. And we just need to multiply 0.625 times 0.5. We get 0.3125, which is 0.3125 out of 10. Again, we can divide 10 by 0.3125, and let's pull that up real quick. 10 divided by 0.3125 is equal to 32. So that's 32, or 32 over 1, which is equal to a 1 to 32 dilution. So ultimately we end up with a final dilution of 1 over 32 once we go to container 1, 2, 3, 4, 5, 6. So yes, container 6 gives us a 1 out of 32, 1 to 32 dilution. In this problem, it says a well labeled well 1 contains 30 microliters of serum. Wells 2 through 6 contains 85 microliters of diluent. A serial dilution is performed by moving 15 microliters of solution from well to well, starting at well 1. What are the final dilutions in each well? So the first thing we want to do is go to well 1 and take out 15 microliters. So we have 15 microliters. And we have our total. So we have 15 microliters divided by our total of 15 plus 85, which is 100 microliters. And we can reduce that to a fraction, which gives us 0.15. And if we wanted to figure out what our dilution is, we can just flip this. We could flip the 15 over 100. We can make this 100 over 15, which gives us a strange number, 1 to 6.6, and I'll round it off 7. So that's our ratio, our dilution ratio for the first step. We do have our multiplier here at 0.15, so that's known as our multiplier. So we can multiply that by 15 and put 0.15 here. If we multiply that, that will give us our next term once we take 15 microliters out. So we take 15 microliters from well 2 added to well 3. We multiply 15 times 0.15. That will give us 2.25 out of a total of 100. And what we're doing here, remember, is we are diluting our concentrate here. So out of the 15 microliters that we're adding, we're getting our concentrate at 2.25 microliters. So it's getting further diluted. And if we reduce that, we would get we have 2.25 divided by 100. To make it a shortcut, since we already have our what do we call it? We have our multiplier. We can just go straight to our dilution. So let's take 100 over 2.25, and that will give us our ratio of 44.44 over 1, which is a 1 to 44.44 ratio. I know these are ugly ratios, but I'm doing this to show that once you understand the math, it doesn't matter what they throw at you. So to get our next dilution that's going to emerge out of well 4, we would take 15 microliters, multiply 2.25 by our multiplier 0.15, and that's going to give us 0.3375 out of 100 microliters total. Again, we are taking 15 microliters out, but this multiplier would tell us our actual amount of concentrate or solute coming out of our well 1, and that's in a total volume of 100 microliters. And if we flip this, 100 microliters over 0.3375, that will give us a ratio of, I'll just write it all out, we get 296.296, which you can round off over 1. So I would just shorten it and say this is a 1 to 296.29 ratio. Yeah, let's keep going. So we'll multiply this again by our multiplier 0.15. So 0.3375 times 0.15 will now give us a small number, 0.050625. It's just ridiculous, ain't it? Over 100. We can flip this, 100 over 0.050625, which will give us, if we simplify that, basically divide 100 by that fraction, we end up with 1,975 over 1, or a dilution of 1 to 1,975. Let's take this madness one more step, and let's multiply by yet another multiplier of 0.15. If we multiply 0.050625 times 0.15, we would get an even smaller number, which is 0.00759,375 out of 100. And we can again rearrange this 0.00759,375, and we divide that 100 by that fraction. That gives us 13,168 over 1, or we would have a 1 to 13,168 dilution. Now I know that seems maddening, but you would be surprised when you get drugs and you have to dilute them maybe 1,000 times, 100,000 times, etc. So that's why you perform these dilutions. So I figured I'll give you a slightly more challenging problem.